Hi everyone, thank you Amir. So my name is Debbie and I'll talk now about some extensions on what Omer just presented to us, some practical extensions basically. I'll give some background in a short talk and then Robert will demonstrate what Omer just presented and one of the extensions I'm going to talk about. So we'll talk about three main extensions that their goal are to capitalize and more exploit further the structure of the radar signal and especially of its sparsity in different domains. So if we look here at our Pulse-Doppler radar signal, what we're going to do, we're going to see three different subjects. So the first subject will be reduced time on target, and what we're going to see is that we can reduce the number of pulses that we send towards a certain direction, and we'll see how which will help us to reduce the time on target to our specific direction. The second extension, and Omer started talking about that, is cognitive radar. So what we did so far is send a wideband signal towards our targets, and we'll see that if we send we transmit several narrowband transmission, we can go further towards cognitive radar. And the third application is MIMO, where we have several antennas at the transmitting part and the receiving part also. So let's start with reduced time on target. So what we saw until now is that we send uniformly impulses towards a certain direction. So let's say each pulse has a PRI, a certain PRI of tau. So you can recover one delay Doppler map in a CPI, a total time of m times tau. So what we're saying is that, okay, let's send some of our pulses towards one direction and the other ones towards other direction. And what we're going to show is that we can recover several delay Doppler maps. So here, two different delay Doppler maps in this example in the same total time, in the same CPI. And what's important here is that we're going to show that we don't lose in the resolution, because here the resolution in the Doppler frequency depends on the number of pulses, and we'll show that doing this non-uniformly and using our specific recovery algorithms, we don't lose in resolution. So let's see how we do that. So if we go back to the uniform pulses that Omer showed us, we see in the blue part the pulse train that we send. We see in the green part the received signal, the pulses that we get back from our targets. And Omer explained to us that the Fourier coefficient embody the different degrees of freedom that we have, the unknown parameters that we want to recover for every target, which are the amplitude, the velocity, and the range or the delay. And what we can do is this Doppler focusing technique that we talked about. So for each Doppler that we focus on, we get a delay-only problem that we need to solve. So we want to solve for this sparse vector x here, and we get a vector problem. So what happens if we do that non-uniformly? So now let's send our pulses non-uniformly. So MP here indexes the pulses that we actually send. So in this example, we send the first and the third pulse, and we don't send the second pulse. And what happens is that the received signal looks like the same without the second pulse that we send. So we go back to the Fourier coefficient, and now what we're going to have to do is to solve this problem jointly in a matrix way, a joint delay Doppler problem, because doing Doppler focusing here will be too much of an approximation. So we'll also, for convenience, assume that our range and Doppler frequency lie on a grid, and we'll solve this as a matrix problem. So we can write our Fourier coefficient as a matrix C here as a function of the unknown parameters that we want to recover. So our unknown parameters are in this sparse matrix A, which contains the L amplitudes that correspond to our different targets, and the location of this amplitude in the matrix correspond to the Doppler and delays that we look for. So this is the matrix, the unknown matrix that we want to recover. On the left side, we have this partial Fourier matrix. We keep only k rows out of the n rows of this matrix, which correspond to the k Fourier coefficient that we sample, just like we did before. And on the right hand, we also have a non-partial Fourier matrix. In this case, we keep only p columns. So the p columns correspond to the p pulses that we actually sent to this direction out of the m total pulses. And this is what we want to recover. We want to recover A here. And the question is, first, how many samples per process? So how big K has to be, and how many pulses, so how big P has to be, we need to recover A when we have L targets. And the answer is, just as before, we need a total of 4L to the power of 2 samples, total samples, where we have at least 2L pulses and at least 2L sample pulses. So this actually breaks the range resolution and sampling rate link as we saw today in Omer's talk. The new thing is that we break the Doppler resolution and number of pulses link here. So how do we actually recover? Because this is the minimal requirements that what we need. So to recover, we're going to extend well-known compress-sensing algorithm from vector inputs to matrix inputs. So we extended OMP and FISTA for matrix inputs. And we can show that our approach basically attains the minimal recovery condition because the partial Fourier matrix that we have actually lead us to attain this 2L and 2L minimal conditions. So just some results. So we see here delayed Doppler recovery using non-uniform pulses. So we use 1/10 of the number of samples per pulses, and the total number of pulses here was 100, and we see different curves for different number of pulses, 50, 20, and 10. So I said that this would help us to reduce the timer target. So let's see that now. So here what we see is that in the left graph, we see that we sent 50 pulses out of 100 to 2 different directions. And in the right-hand graph, we see that we sent 25 pulses to 4 different directions, and we see that the recovery is quite the same. So what we could do in one CPI, in one total processing time, instead of recovering just one delayed Doppler map, we can recover 2 or 4. So this was for the first extension. The second extension is about cognitive radar, and Omer started giving us the motivation for that. So we know that in communication, several narrow bands are occupied, and if we want to coexist with those narrow bands communication signal, our wideband radar pulse can't be the solution. We need to be more dynamic. So what we're suggesting is only transmitting several narrow bands that are spread over this wide spectrum, but only several narrow bands. So how can we recover the delayed Doppler map from this band? So actually what we've been doing so far is basically that. Using our sub-Nyquist recovery techniques, so what Omer showed, or what I just showed here, we only need these several narrow bands. This is only what we sample, so we can just transmit only them. And if we do that, we actually coexist with the existing communication bands. And this leads us to cognitive radar, which is a radar system that has to adapt both its transmission and its reception capabilities, and this is exactly what we do. So instead of sending the whole wideband signal and only sampling several bands, as we did so far, we only send what we're going to sample. And this makes us a lot more dynamic, and the recovery process is exactly the same. And we don't lose anything. So by transmitting only the bands that we're going to sample, we only basically win. And it gives us an advantage in radar jamming and deception because we are a lot more dynamic. We can move our bands in different locations this way, and we can always recover. So let's see that in simulation. So we'll look at 4 different cases of targets, and we focus on hard cases where our targets are very close, both in terms of delay and Doppler. We will check our algorithms in 4 different band combinations to show that the actual location of the band is not important. And we see in the results that the performance of the 4 different bands are the same, and then actually outperform what happens with the wideband signal, because this system is inherent ISNR, because we only, all the power that we have, instead of transmitting it over the wideband spectrum, we only transmit it over the bands that we are going to sample. So we don't harm resolution because we didn't change anything. We sample the same thing and we cover the same way. And so basically we get better performance without any trade-off in this way. And Robert is actually going to show us this demo, this cognitive radar demo, in a few minutes. So before we move on to the demo, the last extension that we worked on, actually David worked on this past year, is MIMO radar. So in this case, we consider different, several antennas transmitting and several antennas receiving. And we'll have different waveforms in each antenna, and we consider in this work collocated architecture, which means that our antennas are close to one another and they see the target the same way. So what happens here? We have M antenna transmitting, we have, let's say, Q antenna receiving, and we have different targets in the space. So what happens is that we send, each antenna sends a unique pulse towards the target. The pulse is reflected back by the target and collected at the receiving antennas. So the signals that we receive look this way. We have here a double sum. The first sum is over the target, and the second sum is over the transmitting pulses, the number of antennas transmitting. So this is the signal that we receive at a certain, let's say, Q antenna. And we see again that our degrees of freedom, our unknown parameter, which are the amplitudes, the delays, and the azimuths, are embodied in the signal. And this is what we want to recover. So our goal is to estimate or to recover the range or delay and the direction or azimuth. So to do that, we are going to base ourselves, and this is what also traditional MIMO does, is coherent processing of the channel. So a channel is a signal coming from one transmitting antenna to a specific target back to a receiving antenna. So what limits us here is the resolution. So the delay resolution depends, as before, on the sampling frequency, on the bandwidth of the signal. It's 1 over the bandwidth, and if we want higher resolution, we need higher sampling rates. The angular resolution, so in the azimuth, depends on the number of elements, the number of antennas. It's 2 over m times q, which is the product of the number of antennas. So if we want higher angular resolution, we need more elements. So basically, when we want higher resolution, we have a more complicated system with more elements, with high computational load, etc. So we want to reduce this, we want to break this link, and we ask the question, can we break the link, as we did before, between resolution and sampling, both in the time and spatial domain, where spatial domain denotes the number of elements, the number of antennas. And the answer is yes, again, using sampling. So what we do here, we go back to looking at the Fourier coefficient again, and we see again our degrees of freedom, our the parameters that we want to recover, and going again to the matrix form. So after separating the different channels that we talked about, we can write this Fourier coefficient into matrix form. And we have here in the middle the matrix, the sparse matrix that we want to recover with the amplitudes at the location depending on the delay and the azimuth. And on the left side, we have the Fourier matrix depending on the delays, and the right side, Fourier matrix for the azimuth. And again, we are going to take this matrix, and instead of taking the whole matrix, we're going to look at partial Fourier matrix. So we take only several rows of this matrix, which denotes the samples that we actually take. And on the right side, we are going to take only several columns, which means that we only take several antennas, several elements. So we reduce the number of antennas, and we keep the resolution. And now the question is, in order to recover again, how many samples do we need, and how many channels, how many elements do we need? And As before, we ended up with this conclusion that the number of samples per channel is also 2L when we have L targets, and the number of elements, the product of the number of elements is also 2L. So again, we broke the link between resolution, range resolution, and sampling range, and this is what we saw before. And here, what is new is the link, breaking the link between azimuth resolution and number of elements, or spatial sampling. And more results about the case where we have noise. So this is the RRP result in the case where we have noise, and the number of elements we need, and the number of samples that we need in the case of noise. So last slides are a few simulations. So first simulation, we have here 10 targets, and we can recover all of them using half the number of receiving elements, transmitting element, and samples. Let's look at a more difficult scenario when we look at close targets both in azimuth and in range, and we're also able to recover them even though we have close targets. So all of this is done at 12.5% of the number of samples comparing to Nyquist total. More simulation, so we see here the conventional, so the blue one is conventional, is Nyquist. The red one is our approach when we don't equalize in terms of power, but if we use the same power in both compared to conventional, we get the green curve, so we're actually getting the same performance. So just to summarize, so what we saw without this talk and Omer talk is that using sampling, we can actually break the traditional link between range resolution and sampling rate, between Doppler resolution and CPI, the total processing time, between angular resolution and the number of elements in MIMO. We saw also that sampling allows for a dynamic adaptation of both the transmission and received signal, leading us to cognitive radio. And this is the only win without any compromise, because we get IRSNR in this case. So thank you very much, and Robert will show us the demo in Pareda.